Deconvolution is the topic of this next lecture. It's the fourth in a series on the subject of wavelet processing. Deconvolution, like Designature, is a wavelet processing technique primarily designed to collapse the long distorted source wavelet into a sharp pulse so that the resolution and the variation in the resolution in the seismic trace can be increased and the variations in the reflection character can be stabilized on different traces. In our realistic convolutional model of the seismic trace, the terms that deconvolution is going to operate on involve the reverberations and instrument effects and the shot wavelet as modified by ghost. This is the same basic wavelet terms that Designature operated on as well. However, deconvolution takes a slightly different approach to wavelet processing in that it also attempts to compensate for some of the time variant wavelet effects, namely, in this case, some of the time variant absorption and also some of the time variant transmission losses. However, the primary targets of the process are the removal or collapsing of the source wavelet as modified by ghosts, the effects of the recording instruments themselves that also distort the shot wavelet, short period reverberations that also distort the shot wavelet, and to some extent time variant effects like absorption and transmission losses. The deconvolution process is applied on a single trace basis as opposed to Designature, which designed a single inverse filter over an entire shot record. Deconvolution filter design is done on a trace-by-trace basis. Indeed, sometimes it's done time variantly on a single trace so that it's to effect time variant deconvolution. Before we proceed, let's review some of the sources of distortion in the seismic trace. Here we have a shot wavelet, which is usually very sharp in the time domain. The effect of adding ghosts, that is the bounce off the near surface layer at both the shot and receiver ends, broadens the wavelet out some more. It also puts notches in the spectrum of the shot wavelet in the frequency domain. Reverberations further complicate the matter, make the wavelet even longer. The reverberation series is an unending series of pulses that follow each primary pulse. The effects of the recording instruments themselves narrow the bandwidth to some extent and make the wavelet look more complicated. And some time variant effects like absorption and transmission losses further reduce the bandwidth so that the total effective shot pulse is this very long and broad wavelet in the time picture rather than the sharp pulse that originally came out of the air guns or from the dynamite blasts, etc. What are the effects of all these distortions on the seismic trace? The effect of the distorted source wavelet is illustrated on this slide. Here we have a shot and a detector on the surface of the Earth. The sharp shot pulse that we put into the ground is illustrated here. The distorted effective shot pulse is illustrated over here, where all the distortions due to ghosts, reverberations, the instrument effects, and to some extent transmission and absorption effects have been included. The energy from the source goes down into the subsurface and is here reflected from two reflectors, call them A and B, and then returns to our receiver on the surface. The effect of the distorted wavelet on the trace can be seen through the convolution process, where this distorted wavelet is weighted by the magnitude of the reflection coefficient at A and delayed to the reflection time at A, as sketched on this trace here. That same distorted wavelet is weighted by the magnitude of reflection coefficient B and delayed to the reflection time B. And the process of convolution is equivalent to summing these two traces that are the weighted and delayed superposition of the effective source wavelet with the Earth's reflectivity. When we add those two together, then we get the recorded trace that we detect here on the surface of the Earth. The goal of deconvolution is to undo this convolutional process. That is, from this recorded trace, design an appropriate filter such that when that filter is applied to the trace, the output will be a sharp pulse where in this case, the onset of the output pulse corresponds to the reflection time for these two reflectors. In other words, deconvolution will allow us to get better resolution in our process seismic trace. On the raw trace, it's very difficult to distinguish the two different reflectors. On the deconvolved trace, we can easily recognize two distinct reflection events. In order to understand how deconvolution is able to accomplish this, we need to look a moment at autocorrelations. The deconvolution process makes use of the autocorrelation of the trace, or in some cases just a trace segment. The importance of the autocorrelation is that it is a condensed time domain representation of the amplitude spectrum of the trace. In order to understand a little more about autocorrelations, let's go through a simple numerical example. Here we have a small trace segment. We only have 4 sample points on it, just so we can go through the numerics of how one actually computes an autocorrelation. So our little trace segment here, call it S of t, has the values 1, 2, -1, and the last sample is also -1, corresponding to arbitrary time 0, 1, 2, and 3. The autocorrelation is formed by correlating this trace with itself. In correlation, one cross-multiplies each sample on the trace and then adds all those products together. When the two trace segments are undisplaced relative to each other, then this is called the zero lag position. So the value for the autocorrelation value that we're going to compute first corresponds to the zero lag value, or the undisplaced position between the two traces. If we cross multiply each sample value, in this case 1 times 1 plus 2 times 2 plus -1 times -1 plus -1 times -1, then that resulting sum is a value of 7. So the zero lag autocorrelation value for this particular trace segment is 7. To compute the next point in the autocorrelation, we displace the trace relative to itself by 1 sample period. For parts of the trace where we have no information now that we've displaced it, we just use a 0 value. So the autocorrelation for a lag of 1 sample is the sum of 1 times 0 plus 2 times 1 plus -1 times 2 plus -1 times -1 plus 0 times -1. All those things summed together give a autocorrelation value of 1 for the first lag. Likewise, we can carry out the process for 2 lags if you cross multiply each sample on the two different traces and add the sums together, add those products together, you'll get a autocorrelation value of -3 for the second lag. Likewise, do the same thing for 3 lags. In this particular case, it turns out to have a value of -1. It's important to notice that if we were to displace this second picture of the trace in the opposite direction, that is, displace it to the left here, so that we compute the autocorrelation value at a lag of -3 instead of 3, then we get the same value that we did when we did computed a positive lag. Same is true for all the other lag values. That is, the autocorrelation is a symmetric function. The autocorrelation value at 3 is always equal to the autocorrelation at -3, or any other lag for that matter. So if, for this particular case, our small little trace segment, the autocorrelation function for this trace segment looks like this. It has a big peak value. In fact, the 0 lag value is always the largest because the trace looks identically like itself at 0 lag. And then it generally falls off on both sides and gets very small at large lags. It's also symmetric about 0 lag. If the trace that we're taking the autocorrelation of is completely random, then I think you could realize that you'll get a big peak value at 0 lag because the trace looks just like itself. But at any other lag, if it's really truly random, you'll get a very small autocorrelation value because the trace doesn't look anything like itself. The autocorrelation function is a measure of how much a trace looks like itself at certain time displacement corresponding to each lag value. The autocorrelation of a completely random function is a spike. That is, we get a big value in the middle. It won't look anything like itself at any other lag, and so you'll get essentially a 0 or at least a very small autocorrelation value. The autocorrelation value function is useful in deconvolution because it's a measure of how much a trace looks like itself at various lags, that is, at various time shifts. Let's see how that's relevant by looking at a reverberation series. Here we have a simple reverberation series that starts out with unity value corresponding to the primary detection of a pulse. Then the reverberatory pulses then follow it at times corresponding to the reverberation period, and the subsequent pulses are alternate in polarity and get smaller and smaller in amplitude with increasing powers of the reflection coefficient. We have -1 here, a plus r squared here. The next term in this infinite series would be a minus r cubed, etc. If we convolve this reverberation series with a distorted seismic pulse, then we'll get something like this trace that's sketched here in the middle, where the primary event is noticeable up here at the prime unity point in the reverberation series, and then other reverberations follow at later times. If we take the autocorrelation of this trace, we'll get a big response here at 0 lag. Here we're just looking at one side of the autocorrelation because we know it's symmetric. The same thing occurs over here on the other side. We'll get a big response at the 0 lag value because this trace looks exactly like itself at 0 lag. Get some relatively small values in between here, but at a lag corresponding to one reverberation period, we'll get a pretty good response in the autocorrelation function because the trace starts to look like itself again at each reverberation period. Likewise, there'll be another secondary peak in the autocorrelation function corresponding to the second period in the reverberation. If we wanted to remove, or if this trace had no reverberations on it at all, then we would get a very sharp autocorrelation function about zero lag and wouldn't have these secondary peaks. Deconvolution requires that we design a filter to apply to the data to collapse the distorted wavelet, which includes, among other things, reverberation. The way this is done is to take the autocorrelation of the trace segment to be deconvolved. Then we'll design a filter to produce the desired output. We'll come back to what that desired output is in just a moment. Apply the filter to the data, and then repeat the process for the next trace or another gate in the same trace to effect time variant deconvolution. The autocorrelation of a trace contains information about that pulse shape or the effective wavelet that's common to all reflectors on the trace, and it also contains information about reverberations. Let's look at some different types of deconvolution. First of all, there's a type called whitening or spiking deconvolution. The goal in whitening or spiking deconvolution is to produce a spike on output. That is, to determine that long distorted seismic pulse and reduce it to a sharp spike. Another type is called gapped or predictive deconvolution. It's categorized as being non-whitening. It tries to collapse that long, effective, distorted shot wavelet into a much sharper pulse, but it doesn't really try to collapse it to a spike. And the third type, which is similar to gap deconvolution, is shaped or band-limited decon, which is also non-whitening. We'll discuss these first two a little bit more in detail. Here we have illustrated the procedure for whitening deconvolution. We'll look at what's happening in the time domain and also in the frequency domain. The input to whitening deconvolution filter design is the autocorrelation of the trace segment that we want to deconvolve. The autocorrelation contains information about the wavelet shape that's returned back from each reflector in the design gate. And this wavelet shape can be quite long and include several reverberations if we allow the autocorrelation to be computed over a long enough time interval. We compute a filter such that when this filter is applied to the data, or if this filter were applied to this autocorrelation, the output would be a spike. That's why it gets its name whitening or spiking deconvolution. The effect in the time domain is to try to make a spike on output. The effect in the frequency domain is to produce a flat or white spectrum. The inverse filter design for whitening deconvolution is very similar to what we saw in Designature, in that the amplitude spectrum of the filter is essentially the inverse of the amplitude spectrum of the wavelet we wish to remove. In Designature, this amplitude spectrum of the wavelet that we wish to remove was determined from a spectral average over a shot record. In deconvolution, this amplitude spectrum is determined by taking the autocorrelation, which is a condensed time domain representation of the amplitude spectrum of the wavelet. And actually the output is to a spike is never completely realized, because there is noise in the data which limits our ability to collapse totally back to a spike, and because we can only deal with the filter of some finite length also affects the result. But in general, whitening deconvolution will result in an output which is very sharp but not quite a complete spike. Just to illustrate whitening deconvolution as applied to a trace, think of this series of primary reflectors corresponding to the Earth's reflectivity that's been convolved with a distorted seismic pulse that includes some reverberations. As illustrated here, we take the autocorrelation of this trace or trace segment, then the reverberation series show up. Also contained in this autocorrelation is the shape of this distorted pulse. We design a filter which in general should be at least one, or in some cases maybe two, reverberation periods in length in order to effectively de-reverberate the trace. Design this filter on the basis of what it takes to collapse this autocorrelation to a spike. When we apply this filter to the trace, then we'll get an output trace that has very sharp pulses corresponding to each of the primary reflectors. All the subsequent reverberations and long distorted pulses have been collapsed back into sharp pulses. It should be pointed out that deconvolution will output a minimum phase output, that is, it's a one-sided wavelet that has most of the energy concentrated toward the front. This is opposed to what Designature would output, which outputs a zero-phase wavelet, which concentrates the peak of the energy at the onset of the reflection. The other type of deconvolution that we mentioned earlier is called gapped deconvolution, which is a non-whitening process. The input to gap deconvolution, as in spiking decon, is the autocorrelation of the trace segment to be deconvolved, and here's its characteristic amplitude spectrum. We design a filter from this autocorrelation, but the significant difference here is that we leave a gap or a series of zeros in the filter between the initial filter point and then the rest of the live filter points. The motivation for doing this is so that the output will not be a sharp spike, but rather a wavelet of generally a characteristic length that's determined by this gap. For some data, like vibrosize data that's been correlated, it's preferable to get control of the output wavelet length, and we do this by specifying this gap rather than trying to do the impossible and collapse the distorted pulse back to a sharp spike. The output wavelet is not really the first few points in the autocorrelation here, but the information contained within that does determine what sort of wavelet shape we get on output. The effects of gap deconvolution in the frequency domain is to smooth the amplitude spectrum of the wavelet rather than completely whiten it. The amplitude spectrum after the application of gap decon is generally a smoothed representation of what the input was. We've taken out a lot of the notches and the rapidly changing aspects of this spectrum. Gap deconvolution is effective for dereverberating so long as this gap length is less than a reverberation period. The application of gap decon is illustrated in this diagram. We have a series of primary reflectors, just as we did in the illustration for whitening or spiking decon. The seismic trace is the convolution of this reflectivity function with a distorted shot pulse. We take the autocorrelation of the trace, which shows up the reverberation periods again, and then we design a filter which has this gap characteristic. The resulting output trace will not be spikes. They won't be nearly as sharp as of pulses as in the spiking case, but they'll have a noticeable length that's generally about the same as the gap length. But so with gap deconvolution, we lose a little bit of the resolution that we would get had we applied spiking deconvolution, but there are some adverse effects as well. We'll touch on those in just a moment. Let's examine the signal-to-noise ratio aspect of the two different kinds of deconvolution. Here we have an amplitude spectrum for a particular seismic trace. We're going to examine what happens to it for the case of whitening deconvolution and for the case of non-whitening or gap deconvolution. The signal-to-noise ratio generally varies over the spectrum, being the smallest on the ends. The noise is essentially flat. The signal spectrum has a lot of character to it. When we apply whitening deconvolution, the process has no knowledge of what's signal and what's noise, so it really flattens the total spectrum. This has the effect of boosting the noise relative to the signal in those parts of the spectrum where the signal-to-noise ratio was small. On the other hand, for non-whitening deconvolution, which essentially just shapes the spectrum, doesn't whiten it, the signal-to-noise ratio is virtually unchanged. On output, in the whitening case, we get a much sharper wavelet, but we also get a much noisier output trace. For the non-whitening case, we don't have nearly quite so much the resolution because our output wavelet is broader, but we have the added benefit of not having elevated the noise. Just to summarize some of the aspects of deconvolution, a different filter is designed for each trace, and sometimes several filters are designed for a single trace in a time-variant manner. The deconvolution process assumes, just like designature, that the input is minimum phase and it will also yield a minimum phase output, which is something that's different comparing deconvolution with designature. Designature will produce a zero phase output instead of a minimum phase output. Whitening or spiking deconvolution results in maximum wavelet collapse for whatever filter length is used and whatever noise conditions are present. On the other hand, gap deconvolution results in less wavelet collapse, but has the added benefit of not boosting the noise level so much.